Okay, next claim I want to make is that we already have that natural numbers crossed with natural numbers, or Cartesian product, is countable. I also claim that set of all integers is countable or denumerable. I'm going to take for granted at this point that z is infinite. Recall, z is the set of natural numbers, so I'm going to write it out as -3, -2, -1, 0, 1, 2, 3, and so on. When you look at this set, it's as if I listed them, but in fact, I really didn't start anywhere. I said, let's go off in this direction in the same pattern, and that direction in the same pattern. To be listable, I'll put air quotes around that. In other words, to be countable or denumerable, I need to say, what's my first element, second element, third element, and so on. Okay, so what's the process here? Similar to what I did with the diagonalization, I need to start somewhere so that if I continue that pattern, I collect all of the elements of the set. So if I start here and call that my first one, and go here, second, third, fourth, fifth, and notice how bouncing back and forth, if I continue that process on, I will end up getting all of those. So it's clear, this is a proof by picture, not a valid proof technique, by the way. I would actually have to write out the formal bijection. But you can see that by continuing this process in order, I'm going to collect all of them, it lists it out. So I'm going to say z is denumerable by that reason. Okay, there. Let's talk about some other sets and other relationships that involve countability. Let's let S and T be sets such that T is a subset of S. Remember, my serifs mean that that's a capital S, okay? And just like I said at the end of class last time, you remember that if T was infinite, this implied that S had to be infinite. And if S was finite, this implied that T had to be finite as well. Just depending on if the larger set's finite, then any subset of a finite set's finite. And also, if an infinite set is a subset of another set, that set also has to be infinite. Okay? Well, that kind of relationship also carries over to talking about countable. That is, if the larger set is countable, meaning it's either finite or denumerable, then the smaller set has to be countable. Okay? If S is countable, then T is countable. And the converse of that is, in fact, also true. If T is uncountable, then S is uncountable. I'm going to not do the proof here just because of time more than anything else. I guess since it's a video, I could probably throw it in there. But I'm also not going to ask you to use anything similar to this proof, so I'll just reference the text. Appendix B. I'm going to get through this so we can start doing some of the real analysis, starting in Chapter 2. So let's just make sure we're familiar with a couple of other useful facts about countability. In fact, this theorem that I'm going to establish here makes it a little bit easier to establish countability. Because in the definition I said there was a bijection, but it turns out that we can actually get away with just being a surjection or an injection depending on which way you're going. Which set is mapping onto which set. Let me illustrate. The following statements are equivalent. Okay? A, S is countable. B, there exists a surjection from, now here's where you got to be careful. Surjection means onto, so there's a mapping from one set onto another set. So if I can take the natural numbers and form a map from here that hits every element of S, then it's denumerable, or then it's countable. Okay? So I don't have to have 1 to 1 if I'm going from N to S, right? I could have several of these go to the same element over here, but as long as I can get from this set and completely cover, that is completely mapped to every element of this set, then it's countable. And I can also get away with going the other direction, that is if I can find an injection, which I don't like that word, but I could call it an injective mapping, but it's just more to write. An injection from S into the natural numbers. That is, I take the elements of this and can form a 1-to-1 mapping to elements of this so that every one of these maps somewhere in here uniquely. It doesn't have to cover the whole natural numbers. That is, it doesn't have to be on 2, but it does have to be 1-to-1. Okay? If you got either this or this is sufficient to establish that it is countable. Okay? And the proof of this one's in the text, in the actual book. It's one of those proofs where you don't have to prove equivalence of each pair of statements. You can do A implies B implies C implies A. If you prove those 3 things, you'll show that these things are equivalent. And it's actually not too hard to do. It's in the text, but I'm skipping that as well because I got a couple more interesting things that I'd like to cover in this section. So, next theory. Let's say we've got a set of indexed sets that are countable for every m out of the natural numbers. Now, what I mean by an indexed set of sets is that I've got an infinite number of these guys. In fact, I've got a countably infinite number of them, meaning I have A1 is a set, A2 is a set, A3 is a set, and so on, all the way up to infinity. Now, if you have an index set where the index is based on the natural numbers, then the union of all of these sets is, I should say then, call this A, is countable. Now, I don't know that we necessarily define this explicitly, but let me write it one more time. This union would be the set of all A such that A is an element A sub M. Actually, I should say it this way, such that there exists an M out of the natural numbers where A is an element of A sub M. Meaning all the sets, all the elements that are in any of the A sub M's. Okay? Now, what this is basically saying, and this is actually a pretty powerful result, that if you have a countable set of sets, notice that is countable. In fact, it's denumerable. This set of sets is countable because you've got a mapping, you've got an index here where this is the first set that's an element of this set, this is the second set, third set, and so on. Okay? So this is a countable set, right? So what we're doing up here is A is a countable union of countable sets. Okay? And what this theorem then says, and this is the way that I remember it in my head, and you're going to need to remember this as a key property of real analysis, and we'll need this. A countable union of countable sets is countable. Now, that's important enough that I want to prove this. And I certainly can't prove it in this space right here, so I am going to go ahead and take advantage of this half of the board. In fact, I'm just going to come up here and start the proof. Now we know we know A sub m is countable for every m out of the natural numbers, which implies that there exists a phi that is a surjection from the natural numbers onto A sub m. In fact, let's call it phi sub m. And I'm using the previous theorem to say all I really need is the surjection part. I only need that it's onto. Okay? Because if A sub m is countable, then there exists a surjection from n onto A sub m. Okay? And so let's let this index function here be those surjections. Now what I'm going to do is I'm going to define a new mapping in order to help create the surjection that I need from n onto this set here. If I can find such a surjection, then I've proven that this A here, which is a countable union of countable sets, is countable. Okay? This is not actually the one that I need, but I'm going to use this as a piece to get there. C is going to map the natural number cross the natural numbers onto A. Not onto, I don't even know that yet. It's going to be onto, but I need to prove that, okay? So what I want to do now is map this set onto here by the following rule. Now, since it's a mapping of a Cartesian product, it's going to depend on two variables instead of one, where m comes from this set and n comes from this set. The output of this is going to be whatever I get if I plug in n, that is the second element, into phi sub m. That is, I find the output of the mth phi when I plug in n into it. Okay, now my claim is that's a surjection. Now, why is that going to help me? Well, in just a minute, we're going to use the fact that if this is in fact a surjection, I have a surjection from this onto this. I know that this set is countable. So I know there's another surjection that exists from n onto n cross n. If I do a composition, then the composition of both two surjective functions is surjective. So then it'll be a composition of one function I have yet to create with this guy, which will create a surjective mapping from this guy all the way onto here. Okay? Now, follow me. Let me get there first. I got to prove that this is in fact a surjection. So let's let A be any element out of this set. To be a surjection, I got to be able to find something out of here that maps to it. Okay? Well, that's actually not that hard, because if A is in here, what do we know about little a? Little a is in at least one of the A sub m's, all right? There exists an m such that A is out of A sub m, right? And phi sub m, that is this m right here, is surjective. It's onto, so there's something out of this set that maps to this A, okay? There exists an n out of the natural numbers such that phi sub m of n is equal to that A. But this is the output. This is equal to c of m comma n. So that implies that c of m comma n is equal to A. That is, picking any point out of here, I have found now an m, which I know exists because of this being a union, and this n exists because phi sub m is a surjection. Now we have found the pair, that is the element of this set, that maps to my A. So QED, or therefore, C is a surjection. Okay? Now here's where I put all the pieces together. We know n cross n. I hope I'm getting out of the way enough for you to be able to see this whatever I'm recording. This is my first attempt to record using this board in here, so I hope this works, and if not, you guys can criticize and tell me next time what the problem is. But we know this set right here is countable. We've already proven that. And by the previous theorem, there exists a surjection which maps the natural numbers onto that set. Okay, so what I'm going to do is I'm going to find now a function that takes, well actually what I do is I'll take an element out of here, plug it into F, which gives me an element of this set, take that, plug it into C, which gives me an element out of A. That implies that the function C composed with F maps the natural numbers onto A. Since F goes from N to N cross N, and then C goes from N cross N to A, and a composition of surjective functions is surjective. Now, I'm done. I have found a mapping from the natural numbers onto A that is surjective. Therefore, A is countable. Done. The countable union of countable sets is countable. Now, a nice little corollary to this. A corollary is generally a theorem. It's been demoted because it's an immediate result of the previous theorem, but it's still a theorem. If you have any finite family of countable sets, namely A1, A2, out to A sub, we'll do capital N, then the union from M equals 1 to capital N of A sub M is countable. And that's really when this works. This statement isn't valid completely until I've said this, because really what I've proven up here is that the denumerable union of countable sets is denumerable. However, if it works for infinitely countable sets or countably infinite sets, it also, as a result here from this corollary, works for a finite number of sets as well. I mean, one way to get this as immediate result is let A sub n plus 1 out to infinity be the empty set. Then you have this result immediately. Or you can also prove it in almost a very similar fashion as what we've got from before. All right, I'm going to stop, erase, and start the next clip.